Okay, so that's the definition of NP. This was essentially given by Cook and Levin independently, inspired by these optimization problems which seem hard, but yet when a solution is given, it's easy to verify. So yeah, so such problems are called in NP, or NP collects all those problems for which there is a polytime Turing machine M, which given this certificate U can check whether U is the correct answer or not. Okay, so let me mention here that this M is called the verifier. That's the verifier, and this U is the certificate for X. So verifier and certificate, and this blow up is polynomial. Okay, so if you look at the length of U, it's not much bigger than the length of input X. These are the key points of the definition. So let's do an example. So in problem 2, which was subset sum, subset is the certificate, right? You are given T, and what is the certificate of T? It's a certificate subset whose sum is T. So this L that we talked about in the definition, this corresponding L is S comma T, yeah, such that S has subset of some T so on input S comma T, what will the verifier do? The verifier basically guesses this certificate. So certificate U is the subset of S of some T. And verifier M is the Turing machine that given STU. So given S and T and the subset U checks whether U is a subset of S and sigma U is equal to T. That's all. Okay, so verifier M is trivial. It just checks whether U is a subset and whether the elements of U sum up to T. And hence, by the definition, it means that L is in NP. You can check this thing, the other conditions also you can check, that the size of U is smaller than the size of S comma T. Right, obviously, because S was in the input and U is a subset, so its size is upper bounded. So there is no size blow up in the certificate, and M is polytime. So overall what you get is, by the definition you get that this L is in NP. And similarly with 1 and 3. Okay, so all these problems, decision problems, they are in NP by the definition, because we have shown both certificate existence and verifier. Now note that if the certificate doesn't exist, it's a no string, right? So this definition doesn't talk about no strings. It talks about in this way, it's an if and only if condition. So if X is not in L, then there should not be a certificate. Okay, but that is clear. So that's the part which you will generally not care about. But when X is in L, the important thing is that there is a certificate, easy to verify. Yeah, so now let's place NP. So where is NP? So the first claim is that P is contained in NP, and second will be that NP is contained in exp. Okay, that's the placement. Okay, NP is sandwiched between P and exp. Easy part is that P is contained in NP. Any problem that's efficiently solvable also has a certificate and verifier, right? The solver of the problem is itself also a verifier. So that's the trivial part. Slightly more non-trivial is why is NP in exp? There also the idea is simple. You just search for the certificate in the whole space. Okay, and just measure the size of the search space. It will be exponential. So let's prove the first part. So say L is in P. So it is decided by poly-time Turing machine. M. So then for all X, for all input X, X is in L if and only if Mx is 1. Right. So a string is a yes string if and only if this particular solver, this efficient algorithm M, accepts it. Right. This is by the definition of M. So what's the certificate here? You can take the certificate U, which was in the definition of NP. That certificate you can take as the empty string. Okay, the verifier M, think of M as a verifier with empty certificate. So with U equal to with empty U, M can be seen as a verifier. Which means that L is in NP. Okay, so this is the trivial part. P is in NP. Every L which is in P is also in NP. This means that P is a subset of NP. It's a sub-complexity class, if you will, of NP. That's the easy part. Now, but NP may also have hard problems, right? Problems which are much harder than polynomial time, like this subset sum, TSP integer programming. So, what is an upper bound on them? Upper bound are these brute force algorithms which are in EXP. So, let us now do that part. So, now say L is in NP with X in L if and only if there is a certificate U and this verifier M, some verifier M accepts U. Right? Maybe to avoid confusion with the old L and M, let's call it L prime and M prime. So, take a problem in NP and then for yes strings X, there has to be a certificate verifiable by a fast Turing machine M prime, which is the verifier. In time, so time of Turing machine M prime has to be polynomial in n, right, in n to the d, constant d. Okay, so this is what is given to you. This is the hypothesis that comes from L prime being in NP. Now, why is L prime in EXP? That is what we want to show. So, we will look at the brute force algorithm. What will the brute force algorithm do? It will try to go over all the U's, right. So, go over so searching U takes 2 raised to n raised to c time. Right, U is a string of length n raised to c. So, you can search for it. This is basically coming from here. U is in 0, 1, x to the c. As U is in 0, 1, x to the c. So, if you look at the whole space, search in the whole space, then it is 2 raised to n raised to c time. And for each choice of U, you will run M prime and check. That will take n raised to d time. So, brute force algo is two raised to n raised to c many possibilities of the certificate and n raised to d time for each. Actually, what happens is this U is as large as n to the c, right. So, this will take time, slightly more time, it will take n plus n to the c and this thing raised to d, right. So, it takes this much time. So, first the certificate blows up slightly, then when you run M prime on that, I can maybe do it in 2 steps. So, the input of M prime is x and x to the c length. And in terms of the input size of M prime, time is raised to d. So, which you can write on the next page. right? So that's the time complexity, 2 raised to n raised to c times n plus n raised to c whole thing raised to d. But notice that this is still exponential in n, it's not more than exponential. So this is actually less than 2 raised to n raised to c plus 1. Right, you can check this because c and d are absolute constants and n you can take larger. So you check this thing, this is true. And once you have checked this, this finishes the proof. It's an exponential time algorithm. It means that L prime is in d time 2 raised to n raised to c plus 1, which is clearly exp, contained in exp. Okay, so that finishes the second part. Of course, this means what? This means that NP is contained in exp. Okay, because we have done this for every language in NP. So every problem in P is in NP and every problem in NP is solvable in exp. Okay, but exp is not good enough. These are very slow algorithms. These are really brute force algorithms. So that's the open question. It's unknown whether NP is different from the other two. Okay, so you can ask whether P is strictly smaller than NP, and you can ask whether NP is strictly smaller than exp. That's the conjecture which usually we make, that NP is strictly between P and exp. Okay, not all problems of exp can be solved in NP, and not all problems of NP can be solved in polynomial time. But one interesting thing is that these two endpoints, P and X, these we will separate in this course. Okay, so later we will actually be able to show that P, polynomial time, exponential time are actually different classes. So which means that there is a big margin between P and X, and but you don't know whether NP is closer to X, closer to P. Okay, those are the open questions. So what does NP stand for? This we did not. I did not tell you what does NP stand for. So NP stands for non-determinism. So the N in NP stands for non-determinism. Okay, so non-deterministic polynomial time. That is what it means. So why is such a thing called non-deterministic polynomial time? A better name would have been efficiently verifiable. Instead of that, why this complicated name? So to answer this question, we have to define a whole new model, which is called non-deterministic Turing machines. And I think that also you have probably seen in other courses. So we'll shorten this to NDTM, non-deterministic Turing machines, to contrast with Turing machines, which we think of as deterministic. So the definition of this will be similar to Turing machine, except transition function will not be a function. It will be a relation. So NDTM is similar to Turing machine, except that now there are two transition functions. So we have alphabet, states, and two transition functions, delta 0, delta 1. Or you can also think of this as there being a transition relation. So what is the difference between transition function and transition relation? Well, in the function, once the configuration is set, there is only one way to move to the next configuration. In the transition relation, once the configuration is set, there might be multiple ways to move to the next configuration. There might be multiple next configurations. That's why it's a relation. And in fact, it suffices to, as you will see later, it suffices to just assume there are two options. So first option is given by, or let me say 0th option is given by delta 0, and 1th option is given by delta 1. Okay, so function becomes a relation essentially. And so at any configuration C, its transition is no more unique. So it has two allowed moves. So in fact, this NDTM has two allowed moves. One following delta 0, and the other delta 1. Okay, these are the two moves. What now, given a configuration, at which one of these will the Turing machine choose? So that we don't say anything about the choice. Okay, the Turing machine can take any path. There are two paths. and we will only make a statement about what happens in the end of the computation. Okay, so this is a more fuzzy computational model. That's why it's called non-deterministic. It's the steps are not determined like we defined in Turing machine. So NDTM accepts input X if there exists a sequence of choices leading to the accept state. And output 1. That we can set as a convention. Okay, so that's the condition we are putting, that there should be a sequence of choices. So the first choice, say that NDTM makes delta 0, then delta 1, then delta 0, then delta 1, and so on, and reaches the accept state, halts and outputs 1. Then we say that, okay, since there is some path to acceptance, M has accepted X. Okay, so M is not supposed to accept on all the paths, just one path. And what is the negation of this? The negation is all paths reject. Then M rejects. So if there does not exist such a choice, then M is said to reject X and output 0. Okay, so that's the NDTM setting. Okay, there are choices at every step, and if a sequence of choices leads to accept, then output is 1. Then we say that actually it's a yes string. If there is no accepting path, then it's a no string. And now, since we don't talk about how the choices will be made, this is not really a practical computational model. Okay, this is as theoretical as it gets. It's not a practical one. Turing machine is like computers, but this is not like computers. So what's the definition of time? So time taken by M on X is the maximum number of steps by M to halt on X. Okay, so this is a bit sensitive to the steps. I mean, we are looking for we are going over all the accepting paths and what is the longest. Okay, that defines the time complexity of NDTM. So this maximum is over. Oh, this is not just accepting paths, sorry, these are all paths. So how much time will it take to halt? Because remember, if x is a no string, then you have to go over all the paths and see that all of them are rejecting. So actually this is maximum. This is why it is maximum over all the paths. So max over all possible paths. Okay, and based on this, we'll redefine NP next time.